Okay, yes. So we had a Splinter session with co-organizers Lily and Belinda here. And just for people who weren't there, the driving question for this Splinter session was what stellar data sets will allow the community to produce the largest advances in probing stellar variability, developing diagnostics, and assessing mitigation techniques. And then how can we facilitate cooperation among instrument teams, which is why we were doing this here. What we're hoping to get out of this, and we've begun to see, is an initial list of stellar variability touchstone targets, a formal stellar variability working group, and then a white paper that's already, the skeleton is in place, as I will allude to later. So we had 4 talks about sources of variability, the lessons from solar data, what can we do with standard stars, and then what more do we need? And then we had a bit of a radical format for the second half, for the majority of this Splinter session. We broke up into individual groups and each discussed the 4 questions that are there below, and then discussed those and reported back. And so I'll be going through some of the main highlights from each of those 4 questions. So the first question was, what do we want to make sure that stellar variability data sets capture? You can see a word cloud of some of the most common responses. This is broadly grouped into 3 main things. So data properties. So there was a lot of conversation, obviously, about going to the extremes in every single one of these: wavelength, coverage, cadence, and resolution. But there was also some interesting point brought up about how these could be different for each target, and so that's something worth looking into as well. As far as stellar parameters, emphasizing different types of activity and then ranges of spectral types and ages as well. There was a lot of discussion about the auxiliary data for beyond just RVs that could help with these stellar variability RV data sets, photometry, and you can read those up there. Our second question was, what targets should we prioritize and why? And so this was sort of getting at one of our objectives of having an initial list of stars that could be interesting. You can pick out a few fun words like stars are important to look at. So then in general, it seems like the typical G, K, and M, so not really F stars weren't mentioned. Again, range of ages, range of activities. But then some discussion about where these stars could be observable, northern, southern, and then to get as long of a yearly baseline, but then also talking about stars that could be observable by both, which is kind of at odds a little bit. But a few favorites came out: Tau Ceti, Epsari, 3651, Maunder minimum candidate there, and 26965, which has been mentioned a lot here. The third question was asking about our best approach to getting these data sets, whether this would include buy-in from GTO or specific instrument teams, as opposed to individual proposals. Again, you can look at some of the most common words there. And so, yeah, some of the questions that came up, is it fair to put these on, or these sorts of proposals on individual teams? There's some questions, well, do we already have some of these standard stars, and maybe we should focus on the ones that we're already observing and have more communication between teams? There's a lot of discussion about the difference between US and Europe, and some potential funding sources or these survey proposals of interest through ESO. Another point that was brought up was if there's somehow, perhaps through RCN, a way of injecting funding into all of these instruments for something like this. Obviously, we don't have all of the answers to these, but these are good questions. Then underused instruments and telescopes for things like activity indicators, maybe not necessarily focusing on just the EPRV ones, but also just the regular RV ones. And another point that was brought up, I think by a few different groups, was, how will people get rewarded and who will get credit for things like this. And so these are important things to remember. And this third point, I don't know which group, I forget which group said this, but apparently it was mentioned several times that beer is important. So not sure quite what that means. And then the last question was kind of a catch-all. What have we missed? Again, some words there. Take from that what you will. But then, one of the kind of main points was, how do we fund and coordinate efforts across these countries and continents? And this is something that would take a lot of thought, effort, stable funding for long periods of time, both projects and people. And again, focusing on early career researchers and how we can minimize risk for them. There's some points also on simulations and how we need theory to understand our observations, and then observations to inform the theory and how those work together, and then data analysis techniques. So in general, we brought up a lot of questions, and we maybe didn't have all of the answers, but I think getting to a point where we have all of the questions and we know what questions to ask is still worthwhile. And so we'll be working on kind of the white paper and putting this together into something a little more formal. So I think that's it. Yes, thank you.
He's fled before I can ask if there are any questions. We might not have questions. Are there questions in the room for Jacob? Okay, if not, we'll roll on to our next Splinter wrap up. The Build a Better Ruler folks. Ryan, are you giving that? Oh. Oh, okay. Sounds great.
Okay.
Yeah. I take it back. Okay, our second presentation will actually be from the machine learning techniques group, so please take it away.
Hello. Hi. So we have our second day of the machine learning Splinter session. In this day, we have a brief introduction to some generalities of deep learning, with emphasis on convolutional neural networks and autoencoders. After that, we have 3 presentations, which works with different supervised and unsupervised techniques. The first 2 was very interesting, and the third one, not much, because this was mine. After that, we have a very brief discussion with the speakers as panelists and with Alexander Weiss. The topics discussed were what was the primary challenge or barrier in successfully implementing these methods for RV, and we all agree that is the part when we stopped of work with simulated data and going to real data, right? For the step from realistic to real, it's quite a challenge, and making a mistake in the way you implement your model or format your data is challenging because you often never really receive feedbacks from your results that you might be overfitting. In other words, you can make mistakes and you never notice. Another question about interpretability, how we can interpret machine learning results without being experts. Some solutions could be tutorials and templates by professional software engineers, would be very helpful. So we should fund more software developers. We should move towards making all code open source, do the same things that the open source community do. That is, everyone can check your code and validate. For sure, there is another scientist who wants to prove you wrong, so he will test it. Making GitHub repositories and so on. Creating standard templates could be useful, and documentation. And in the end, machine learning is just another tool, and we should be aware that these models are very flexible, but otherwise use standard evaluation tools such out-of-sample performance. So what's the best advantage of these tools? Its ability to deal with huge amount of data, it's a great advantage, and they are very, very powerful to finding patterns. As people who use deep learning, do you believe in modeling away the stellar activity or trying to create physically motivated models? We think there is a balance between physical models versus remove stellar activity blindly. And in the end, we really want to understand the underlying physics and be able to confirm the machine learning predictions, right? With traditional methods such as doing follow-up observation or other traditional activity modeling methods. And the last one, is there any industry practices that we should not use in EPRV science? Generally, no. We should probably use many and industry practices more. However, there's a differences between the goals of industry versus the goals of science. And uncertainties are currently not accounted for in many of these standard models, I mean the industry. Whereas those are critical for doing science, and we usually have uncertainties for every single measurement. So that's all. Thank you.
Questions for Luis in the room? Okay, you're also free to escape. Ryan. I like that you know to just come up and help at this point because we're hopeless. Thank you, Ben. Okay, well, we get set up. Our third report out will be from the Building a Better Ruler, the calibration splinter. Fantastic. Thank you so much.
All right, you can hear me. Yes. All right, so good afternoon again, everybody. I'm here to report on the second day of the calibration focused Splinter session. And I suppose I have a couple of greatest hits from today here to show you, but just sort of in general, I'd like to thank the folks who did contribute talks, and particularly the speakers from the different instrument teams that we had today. And I'll note that the sessions that we had were there was a lot of talks in a row. And so it was very information rich. And I think the video recordings of the Splinter might prove to be a useful resource, particularly useful resource going forward. And I really enjoyed just learning all about some of the nitty gritty details about the wavelength calibration for these different instruments and the ones that we heard about on Tuesday as well. And sort of the ways that folks are dealing with wavelength calibration, the magnitudes of the kinds of problems they're dealing with, as well as some of the new technologies that we learned about, and also the intelligent strategic use of some not so new technologies like emission lamps. So I do think that the presentations and then some of the questions and discussions that were had around those presentations, again, are a useful resource going forward for folks that are potentially interested in looking at different RV results across instruments, or folks who are interested in implementing new kinds of analyses on instruments where you haven't done that before. Yeah, there's a lot of good work that's been done. So a couple of the things that we saw today, there was lots of discussion of the advantages and disadvantages of the different kinds of calibration sources. And it's very clear at this point that even though the laser frequency combs and maybe certain kinds of etalons are kind of the future of calibration, emission lamps still play a really important role for many different instruments. And so we heard a lot about the different ways that those were leveraged, and the use of different calibration sources in the same instrument can get you a very, very long way towards understanding the wavelength calibration systematics that you're subject to. We learned a lot about different wavelength calibration architectures. So there were flowcharts like this describing some of the algorithms that folks used, and there's a lot of I would say commonalities and a lot of interesting differences in the ways that wavelength calibration is actually affected across all our different instruments. And so there's some interesting nuggets in there if you go back and look at our recordings. There was also a lot of nice discussion about where we get to with the wavelength solutions and some of the systematics we see in the residuals, for example, like you see here, and the ways that folks have elected and tried, and sort of the complexity of the parameterizations of the wavelength solution that have sort of needed to be used to get good structure in the residuals, or minimize structure in the residuals, I should say. And at the same time, a lot of work has been done on understanding exactly what does the drift look like in these spectrographs. So once you have the wavelength solution, how does it actually deviate over time? And so we got to see how different spectrographs appear to be drifting over time, and the incredible suppression of the effects of these, this instrumental drift that's actually being affected in many instruments as well. And I would say one of the exciting things looking forward that was touched on in a couple of cases was the power of, in particular, the laser frequency combs to give us information that we can actually leverage about the instrument response functions. And so getting a really good understanding of how your spectrograph response varies over time, and actually using that in your wavelength calibration and in how you're measuring your radial velocities. I think a lot of folks sort of see that as an important step forward, and it's exciting to see that several groups are starting to proceed down that line. So those are some of the things we talked about today. Again, I encourage you to go check the recording if you are interested in digging in more into any of that. And thanks for your attention.
Hey, thank you, Ryan. Any questions in the room for Ryan? Okay, with that, let's thank all of our Splinter report outs again, and our leads of the Splinter sessions who have done such a wonderful job of organizing over the last few days.